I will discuss phase rule in this lecture. Gibbs deduced the theoretical relation between number of phases, number of components and degrees of freedom, also known as the variance. These are symbolized as P, C for components and degree of freedom by F. This relation which Gibbs deduced is popularly known as the phase rule, which is the today's topic. Now, before deriving the rule, it is important to first understand the terms phase, component, degree of freedom. So, phase is defined as any homogeneous and physically distinct part of a system which remains separated from other parts by definite boundaries. If we take gases, a mixture of gases, then we will get only one phase. Since the intermolecular distance is very large compared to their diameter, gases are completely miscible. So it will constitute only one phase. P will be 1. In case of liquid, if the liquid that you have taken are miscible, then they will constitute a single layer. If they are miscible, then P will be 1 for miscible. And if they are completely immiscible, then they will constitute different layers. In case of immiscible liquids, the number of phases will be equal to the number of layers that are found in the system. Since they are immiscible, they will not mix with each other to form a single layer. They will constitute different layers. And you have to just count the layers to find the number of phases. Now, what happens for solid system? Each solid constitute a single phase. And you have to consider also the allotropes and polymorphic forms that will also contribute each. Now, what will you consider for a solid solution, that is alloy? If it is an alloy, then it is not more than one phase must not be considered. Then you have to consider only one phase, since they are completely forming a homogeneous mixture. Then you have to consider a single phase. Next we have component. It is the smallest number of independent chemical constituents by means of which the composition of entire system, that is each and every phase, can be expressed. So if you have water only, then what will be the number of component? C will be 1, and that is H2O. If you have ice, that is the solid form of liquid water, then also you will have C equal to 1, that is H2O. Now what will happen for ice water equilibrium? Here also C will be 1, that is H2O. Only one component defines the entire system. If the equilibrium is like this, ice, water and vapor, then also component is 1. Now if we take copper sulfate water system. Then what are the possible phases? They are solid CuSO4, CuSO4.5H2O, aqueous CuSO4, and we have water in 3 states, possible states. It may be in liquid, that is water, in solid, that is ice, in gaseous, that is vapor. So these are the possible phases for this copper sulfate water system. Now, as component is defined as the smallest number of components which can define the entire system, all the phases, you can easily judge that only 2 components will be able to describe the entire system. For example, if you take the first one, CuSO4, then you will be able to express it as CuSO4 plus 0, this is 0 H2O. If it is CuSO4.5H2O, then you can write here CuSO4 plus 5H2O. If it is aqueous, then you can write here CuSO4 plus n number of H2O. You don't know the number of the extent of hydration, so you are writing here with a variable. And if it is simply H2O, then you will write 0 CuSO4 plus H2O. So with the help of CuSO4 and H2O, that is 2 components, you will be able to express the entire system. So here it is C equals to 2 and it is a 2 component system. Now the third term is degree of freedom or variance. This degree of freedom or variance is defined as the number of factors such as temperature, pressure, concentration, which can be varied independently without altering the number of phases existing in the system at equilibrium. Now for a single phase system, say liquid water, single phase, here you will be able to change both temperature and pressure. These two can be varied independently without changing the state, without changing the liquid phase. So here you have 2 variables that you can change without altering the number of phases. So here F will be 2. It is a bivariant system. Now if ice remain in equilibrium with water, then only you can change only one variable among all. If you change temperature, the pressure will get fixed automatically. And if you change pressure, the temperature will get fixed automatically. Otherwise, this equilibrium will collapse either to water or to ice. That is, if you try to change both these variables simultaneously, this equilibrium will collapse to a single phase system. So here you have only one freedom, 1 degree of freedom. So F will be equal to 1. And it will be univariant or monovariant. Now if we arrive at the triple point of water, then what will happen? It arises at a definite temperature at a definite pressure. If you change any factor, if you change a single factor, then it will collapse. So here you have no variable in your hand to alter that will destroy this equilibrium. So here F equals to 0, no degrees of freedom. That is non-variant or invariant system. Now I will describe this variance, that is degree of freedom 2, what this means, degree of freedom 1, that is you are changing both the variables here, you are able to change only one variable here, you are not able to change any variable here. I will discuss in detail in an upcoming video that will be titled as phase diagram of water. Now we are ready with the terms and we will now deduce phase rule. To start with, we will consider a very simple system in which all the C number of components are non-reactive. And they will remain present in all the P number of phases at equilibrium. So, how many number of variables that need to be specified? You have to find out first. Number of variables that need to be specified to describe the system. One for temperature, another one for pressure, and in the first phase there are C components. In the second phase there are again C components. So in P number of phases there will be P into C number of components. So you need PC number of variables. So total number of variables that need to be specified is PC plus 2. Let us consider this equation for example. You have two variables x and y and one equation. Can you determine the values of x and y from this single equation? The answer will be no. You will be unable to determine the values of x and y unless another equation is given. However, there is an alternative. If someone tells you that I will not give you another equation, you have to solve it in any way, then there is only one option left to you, that is you have to consider an arbitrary value for any one of these two variables. Any arbitrary value. And for that value, the value of other variable will be assigned. So in this case, you have degree of freedom 1, since you are able to consider the value of one variable independently, freely, and the other variable adjusts itself corresponding to that value. So one arbitrary value gives you 1 degree of freedom. Now if I give you another equation like 2x minus 3y equals to 0. Now if we add these two equations, then we will get 5x plus 2x equals to 7x, and these two will cancel out. So it will be 21. It will give us x equals to 3. Now if we put x equals to 3 here, then it will be 6. We take it to the right hand side, so 3y will be 6, so y will be 2. Then we will be able to solve it. Now in this case, if there are two equations, then you will not be able to assign any arbitrary value here, since both the variables are assigned with a definite value. You are not free to assign any value. So here you have degree of freedom equal to 0. So if the number of variables, that is here x and y, equals the number of equations, then the degree of freedom will be 0. And if you have only one equation, that is one equation less than the number of variables, then you will have degree of freedom 1. You have to consider one value. If you have two equations unavailable, then you have degree of freedom 2. So you have to now find the number of available equations from which you will be able to determine the number of variables. This is the first layer, this is the second layer. Now you have to consider two things. One is the mole fraction of the components of all the substances, of all the solutes that are dissolved in the first phase will add up to 1. x1 plus x2 plus ... plus xc, since there are c number of components that will add up to 1, and that will be valid for all the phases. So we can write in this way: x1 plus x2 plus x3 plus ... plus xc equals to 1. Equals to 1. Now this is for first phase. This is for second phase, for the second layer. And this is for the last layer, pth phase. So how many equations we will have? We will have p number of equations. Another thing is that the component that is being dissolved in all the phases will maintain equal potential, equal chemical potential at equilibrium. Since at equilibrium the net transfer of any component from this phase to this phase and back, from this phase to this phase and back, the net transfer will be 0. So the rate of transfer in this direction will equal to the rate of transfer in this direction. This guarantees that the chemical potential of any component in all the phases will remain constant. So we will write mu 1 equals to mu 1 2, means first component in the first phase, first component in the second phase, first component in the third phase, first component in the pth phase. In this way, next it will be mu 2 1, then mu c1 equals to mu c in the second phase, mu c in the last phase. Here it will be mu 2 in the first phase equal to mu 2 in the second phase, mu 2 in the third phase, and here it will be mu 2 in the pth phase. So how many equations this set will give? If we have a equal to b equal to c, then we have two equations, a equal to b and b equal to c. If we have a equal to b equal to c equal to d, we have three equations, a equal to b, b equal to c and c equal to d. So in this case, it continues up to p, so it will give us p minus 1 number of equation. This will valid for the second one also, for this case also. So this will give us c into p minus 1 number of equations. So total number of equations that are available is c into p minus 1 plus p. P from the mole fraction and c into p minus 1 from the chemical potential. Now degree of freedom or variance symbolized as F is defined as total number of variables that need to be specified minus total number of available equations. So PC plus 2 is the number of variables that need to be specified, and the number of available equations is, I have determined just now, it is P plus C into P minus 1. Now simplifying this, we get it will be minus P, PC plus minus minus, so it will be minus PC. This is minus C, minus minus plus, so it is C. Or we have F equals to, this will cancel out, C minus P plus 2. So this is the famous phase rule. I am giving you a homework. Find the phase rule if only one component is missing from only one phase. The rest is same. Say this phase contains C minus 1 component. This phase contains C number of components. This phase also contains C number of components as before. Only one phase is divided of only one component. For this case, try to have the phase rule. This will be your homework. In the next video, I will deal with reactive system. I will solve this homework for you, and I will deal with some critical examples to find out the degree of freedom.